Very good morning, everyone. Thank you for your interest in joining the webinar. I'm Vivek. I'm going to present this session on the design of gravity columns and introduction. So this topic, it shows us to give you an introduction to how to perform more on the nonlinear analysis. That is one of the major requirements for this, as discussed in the codes. Let me take you through some of the slides, and then I will also demonstrate what we have to do in the ETABS for this modeling. So let's get started. So on the design of gravity columns or deformation capability of non-seismic members as per IS 1893 2016, we have this clause discussing that, and it is basically insisting the design is based on the bending moments and shear force resulting from story deformations equal to R times story displacement calculated as per displacements, right? So this is the requirement, and then we also have detailing requirement from 13920. So that is the basis. Now in this presentation, we'll be using the tools and features of the program, the ETABS, of various modeling related tools, as well as many other definitions, which also includes nonlinear cases, nonlinear hinges, right? Interactive database, editing. So everything will be required for this exercise. All right. Yeah. So I have put this slide to discuss, take some moments in discussing the core idea, how we are going to do this, and what are the requirements in terms of analysis and design. So basically, we'll have to do in multiple steps. So 3 steps is to create models. So this requires a multiple model approach. That means you cannot do this in a single model because we are going to change the properties of the structure for different analysis, for the lateral force resisting system and for the gravity frame analysis and design. So there will be a bifurcation. For that, we need multiple model approach. So in the first part, we will have a base model. In that, we'll create a copy of it, and we will identify the gravity frames, beams and columns, and we will release the moments so that they do not participate in the lateral force resisting system. So only the lateral system will be resisting the lateral force applied. And we design the lateral system. So that is step number 1. And then in the step number 2 should be for the gravity columns or gravity frames. So we consider it as a myth that gravity columns will not take lateral loads. So there is no switch that you can turn off the lateral force in the design combinations for the gravity frames, or simply changing it to ordinary will not work. So what code has already recommended us is to ensure the compatible deformation. So the analysis must be done for compatible deflection from the step 1 lateral load analysis. So what we'll have to do is, now we have to create another copy of the model. And in that, we are going to design the gravity frames alone. So this requires the loading to be obtained from the first model, where we have the lateral displacement, unscaled lateral displacement, and that will be multiplied by the R factor. So we'll get the target displacement for which the system will be subjected to. And for that displacement, we are going to design the gravity frames. So this is going to be a nonlinear load case, and we will do that in a nonlinear special nonlinear case in this specific model. And then within that, we will also have to check the hinge developments. Basically, we have to study the hinges from this nonlinear analysis to ensure that the members are not yielding. So there are two parts in this. Part A is designing of the gravity column, and then part B is studying the hinges of these members. So this step 2 is of 2 cases. We will do that. And then in the last step, we will repeat the exercise with 2 times dBE level. And this step will safeguard against the premature failure of beams in shear, as demonstrated in several past earthquakes. So the overall, we need to use a multiple model approach, and we will see this in action in a demonstration model. We'll come back to this slide after we finish the demonstration. Let me take you to the next slide. And I've simplified this workflow as a chart so that you can easily remember this. So we have the base model, and then we create a copy of it for designing the lateral force resisting system. Right? This is the design of lateral force resisting system. And for that, we will release the gravity frame moments. So we have the results of lateral force resisting system, and then we'll create another copy of the base model. And here we need 2 more models. One is to design the gravity column, and another one is studying the hinge deformations, whether the members are yielding or not. So 2 studies are there. One is for design, another one is for hinge. And for this, the loading will be displacement, the target displacement. And this model requires the nonlinear analysis. So on the previous one, this one, lateral force testing, will be a linear analysis. So that's how this is done. Let me take you to next slide and explain about the base model which you're going to use. I would like to switch to ETABS and demonstrate what we are going to do from this model. All right. Now we have the base model. Let me explain the system. So it is a combination of gravity columns as well as lateral force resisting. So in this model, we have the walls as the lateral force resisting system, and all the columns and beams are gravity frames. So that is the assumption for this model. And this model is prepared for the other models that we are going to create. I will explain those as well. So you can see this standard model, typical dead and live loads, and then you have a diaphragm assignments. We have assigned a rigid diaphragm. We need rigid diaphragm for this exercise because we are going to release the moments of the frames, and then this rigid diaphragm is going to hold the system together for the analysis. All right. So I hope the model is very simple and clear. From here, we will also define few more things required, such as groups. I'm going to utilize the group definition, like gravity, beams, and columns, and some lateral force resisting system grouped for easy selection of members for modifications in the subsequent models. Now here we have the load patterns. The standard way of creating the model, nothing special, except that here I'm going to use unscaled seismic instead of the auto lateral load. So I have converted into user loads. So I have performed dynamic analysis, is response spectrum analysis, and I got the story forces from that, and I'm applying it as a user load for the seismic. For X and Y, I have removed all other static and response spectrum cases for simplification so that you'll be dealing with a lesser number of load cases. So you can see this two sets of load cases. One is the unscaled forces, and then another one is a scaled set of lateral loads for the same EQX and EQY load cases. So you'll be using it wherever it is required for strength design, and then for wherever the deformations are required, we use the unscaled one. All right. So all are linear cases. Can run this model and ensure that everything is fine with this model to proceed for the gravity frame design. We'll perform concrete frame and what we are also interested. So everything looks fine in the design. And then we are also interested in noting down the deformation of the unscaled. This is basically the spectrum force distribution unscaled. And this is about 6.5 mm. Okay, let us check for Y also. It is also the same because the building is symmetric. From this base model, I'm going to create the first for the lateral force resting system design. I will rename it. Right. All I have to do is release the frame in moments and perform the design of the lateral force resting system. So for that, we'll use the group, select the beams first, and then assign them with torsion and major moment releases. Then I will select the columns, gravity columns, and assign them with M2 and M3, both the top and bottom. And that's it. Now we can perform the analysis. For that, let me check the load cases to run. We don't want all of this. So we need the scaled. So I will turn off the unscaled. So this is strength design. So did the gravity loads, then the lateral loads, the scaled ones. Right. And under the load combination, you can see the default combinations generated. using the scaled. You can run the analysis and then go ahead and perform the lateral force resisting system. In this case, it is only the walls. Here, wall design. Then we'll perform the design. Right. Now here you will see the walls are safe, and then we note down the reinforcing ratios, approximately 2%, 1.2, then 0.6, 0.25. So that's the variation. So at the base, importantly, it is about 2% that this information is needed in the subsequent models. Now let me open base model once again. And this time I'm creating another copy for the gravity frame design to save as, then base model and suffix it with gravity frame design. From here on, we'll be dealing with nonlinear case definitions. So we will be using the unscaled displacement, and then we'll be updating the combinations for that. We just go back to the combinations. What we'll have to do is, so we'll be using the unscaled one. We'll be using this and we will have to convert this linear static case to a nonlinear static. So before doing that, we need to few more things, so which you can do it in ETABS itself. Otherwise, you'll be having to deal with lots of manual definition of load combinations. So you can see in each linear static case, there is an option under the load case. It's called design. Change this into seismic. And we don't need the scaled ones anymore. So I will modify this design type to other so that program will not be able to include them in the design load combinations. So that the design means for the design load combinations, right? From here on, we are going to use the unscaled one, the displacement, right? And then now I'm going to update the load combination with the new set of, I will do concrete frame design, just convert in user, just in case we want this to edit. and then I will create. You can see the 14 combinations created, and specifically on decon ST, starting from here, you will see the scale factors as per Indian code, and then it is using the unscaled, right? But note the force distribution is based on the unscaled, but the displacement is the key for the analysis, the target displacement, which will be 4 times, which is the R value used in the base model. The displacement 6.5 mm we know. So it is about 26 mm. So this step is required to update the load combinations before I convert them into nonlinear static cases. So now I'm going to work on the load cases. So this particular case, unscaled one, we'll modify this, and you see this load case type, we are changing this from linear static to nonlinear static. And then load application is not the loads. Please note the loads applied here is only significant in defining the load pattern distribution along the height, not the actual magnitude of the load. So the magnitude of displacement is the key. That is what we are specifying here through this, from changing this full load to displacement control. And the monitored displacement value of 26 mm, 4 times 6.5, or the R times the displacement, unscaled displacement. So 26 mm. And the monitored displacement for this case is in the X direction, which will be in U1, and story 4 is the top story. And you can select any particular joint from the label to be monitored. That's all. Now you can see the update here happening. Same we will do for Y direction. Displacement control, then same 26 direction U2 for the Y direction. All right. Now for this, we are subjecting the gravity frames for this displacement through this analysis case, and we don't want any participation from the lateral force resisting system, which are the walls in this case. So what I'm going to do is select these walls, so LFRS group, and change the property of this wall to none. Right? And then we are going to assign roller supports at these locations. Now interest rates, roller, set. Now we will ensure the load cases required for this. We don't want the scaled one, but you can note the nonlinear static and the gravity. These are the cases required here. Right. You can see the displacement of 26 mm as specified as the target displacement for this load case. And can also see forces induced by this displacement in the frames. And also in the combinations as we have defined. All right. Now we can go ahead and perform the design of these gravity frames. And one more thing I have done is converted these gravity frames for the design from ductile to ordinary. And then I start the design and it's complete. Sorry, the design is complete and the results are available to review. Now you can take the design of the columns from here, but it is only half of what required for this design. So we'll have to study the hinges as explained earlier. For that, I'm going to create a copy of this. So that will give the green signal to proceed with the design results found here. So I'll do a save as of this design. Now I'm going to suffix with hinges. Right. So here we are going to only study the hinges. No design is performed. So it is all about the analysis and the hinge assignments that we are going to make. Now, I've been talking about the word hinge. So let me introduce you to the hinges. So hinges basically define the post-yield behavior or the moment curvature or moment rotation relationship that will be used to describe the post-yield behavior, whether it can be beam, which is subjected to bending moments that can yield, or for columns, it will be interactive axial and biaxial moments, P, M2, M3, or for walls, uh, have P and M3 interaction, right? And we can also have shear hinges to study the shear failures, which is also a key failure mode that can be expected from this gravity frame analysis and design. So for all of this, we have two options. One is the user-defined hinges, which is available under the define. Frame wall nonlinear hinges. The another one is program is already having the FEMA 356 based auto hinges through the ASC 41 code, which is also readily available to use in this. So I'm going to use both of them. So one is for the shear hinge. I'm going to define it manually. So you can show it here under the section properties, frame, wall, nonlinear hinges. So I'm going to do several definitions and assignments. So let us take some time in this, because this is the analysis is going to give you the green signal to use the gravity frame design. So I'm just reiterating that statement once again to emphasize the need of this analysis. So let's define a new property. We have concrete type, and we can label it as V2 for major shear for beams. So this shear, we're checking on the beams. We can select shear V2 hinge, and I'm leaving it to the yield force internally calculated by the program. Should be sufficient. So a discussion on this itself uh, would be a webinar separate from this. So I'm simplifying by using the default hinge definitions. So I'm having this V2. That's how a user-defined hinge is defined. Now we need another set of information, which is called the rebar. The rebar in the members. So this is handled by the program two ways. One is either you can define sections when you define the frame section, whether it's a beam, let's say this particular beam, and under the reinforcement. So here on the right side, you will find this reinforcement area overrides for ductile beams, but this is also used in these cases where the reinforcement is specified by the user. So if I detail this for 1000 mm square, I can put 1000 mm square, and this rebar at the top and bottom at the ends will be used in this analysis. If it is 0, then the program will look for the design results to perform the design, or else it will use a minimum value of about 0.3% internally to get the rebar data added to the model when you run the analysis. So primarily the two, one is either you specify it here. It depends on the project. You can specify it here, or in this case, I'm going to use the design results of the gravity. So I'm going to run the analysis one more time without changing anything further. So a similar definition for the columns, like how you define the rebar configuration inside the column section. It is the same result as the previous one where we designed the gravity. It is the same result. We just created the copy, and then program handles it nicely like this. Once you perform the design, right, the design results are retained till you run the analysis again or you reopen the model. So program holds this design till that. So that I'm going to utilize this. So that way my rebar information is already available to these members. However, for the columns, we will be typically assigning this as ratios, which we'll have to do. And I will also have to remodel the walls, which is the lateral post resting system. So for that, I will simply unlock just to show you what's happening here in the design. You can see the design results are still available. It is not lost. So if you press delete design results, it will be lost. Internally, program holds it for you. That is sufficient. And now we are going to update the walls. I'm going to select the LFRS and assign them with the wall section, replace it the original section. And then we'll update the reinforcement for these walls. So save some time, I'm going to apply same rebar ratio from bottom to top. You can update it manually, different story height, the levels with variation in the rebar. But here you find reinforcement for wall hinge. I'm going to specify it directly as a ratio as 2%, what we noted down in the LFRS design, 0.02, and the rebar material is 500. So typically the provided the detailed rebar, say about 0.8%, and we will apply this. So reinforcement are updated. Also right click, rebar ratio specified here. Yeah. And now you'll be start assigning the hinges for all the members, including the lateral fortressing system as well as the gravity frames. Let us start with the walls. Create previous selection, and then we'll go to the assign shell wall hinge. And here are a couple of options. We'll go with the vertical shear wall with auto fiber hinge. You can see these are applied. Next, we will select beams, then assign them with hinges. And under the hinge assignment, you have some default options. We will use the user defined, and we will start with the shear hinge for the beams. You can specify it at relative distance. And then we will add an auto hinge for the moment, which will be based on ASC 41. So I'm going to use ASC 4113 code for this, and there are predefined hinges that we can use. So concrete beam, it will be moment 3, and the transfer reinforcing is not conforming for our case because these are gravity frames. And then the shear value can be from any particular load combination. We're using the gravity for this. So this is one end of the beam. The other end, we'll put in places slightly away from the shear hinge. So we'll put at 0.1, and another one at 0.9. It will be a copy of the previous one. Can accept the same. Then lastly, another B2, 3.95. We will add this. So two hinges on each end of the beam. One is for shear and one is for moment. Apply. You can see these are getting applied. Let's finish the column. Select the columns and assign them again same hinges. Column, we'll use the auto at the base and one at the top. So we have concrete column and it will be PM2 M3 interactive. And we are interested only in the flexure for this study. And one more at 0.9 relative distance, which is at the top of the column. It will create a copy of the previous one. Can accept quickly that and press. All right. Let's save this and let's work on the load cases. So we already have the nonlinear static case. So no change in this, except for the results saved. We will change this from final state only to multiple states. So we'll get um, the results in multiple state. Let's have this so that we can get the pushover curve. Can reveal many things. Now one more set of which is for the step number 3 to ensure the hinges are not yielding, especially for the columns at the base or at the roof level. So we need 2 times. So I'll create a copy of this previous one. So I'll rename it 2x and the displacement control will update to double of it, which is 52. And same for y direction. US means unscaled and the 2x means 2 times the dB value, 52. Right. We have the 2 sets of data and load cases to run. We'll run both the nonlinear set of cases. One is at the dB level and there is 2 times the dB level. Now we can go ahead and perform the analysis. Yeah, there might be some warnings. That is for the PMO interaction surface is not convex and program was able to adjust it. So similarly, you have 128 for multiple hinges and there are no errors. Yeah, but so it is okay. And now let us look at the deformed shape. Of the 26 mm displacement. And the color coding here on the scale shown below is for the moment curvature relationship. So A to B is not yielded. Just beyond B, B to C, it is yielding and plateauing, and C to D is dropped, and then D is completely collapsed. So it is based on that. I will quickly show that as well. But let us see the hinge formation. So it is at step 0. You can use. Okay, I'm sorry. I will have to rerun the analysis. I forgot to remove the rollers. Just a moment. It is. Select all. The base. Yeah. Now the LFRS is participating. Okay. We go to the deformed shape. Now you can see the displacement. You can see the first yielding of these beams here at about 10 mm. Step number 6, 7, 8, 9. So this is 26 mm. This is for the DB. And this can be found in the static pushover curve result. The plot is readily available. So you can see it from here, and you can see the change of slope in the pushover curve. That means it represents some of the members are yielding, just about yield, just started yielding, you can say, because the color, what we are seeing is B and C. Just to show you what it is, I'm going to go back to the frame hinge definitions, and you can also see show generated props. So this one will show. Now you can see the color coding here, the definition. So there are two outputs you can get in the deformed shape. One is this state. This is the state of this. So you can see the green color is here. It's just started to yield. This is A, B, C, D, and E. Right? That's what you see here. The color coding matches here. The other set is the status of the hinge with respect to the performance criteria, immediate occupancy, life safety, or collapse prevention. Program can display both in the. You can select from the hinge state or status. So in this particular model, so it has just yielded, it is not collapsed. So this is okay, but the beams are expected to yield, but the columns, the gravity columns, have not yielded. This is what we have to see from this. And this output, pushover output, will also give you a table of output that will give you state and status easily. And you can see a number of members have not yielded, like for each step. And then at sixth step, it has started yielded. Two members have yielded, which is between B and C. B and C is the plateauing, just not collapse. So this is okay. And none of the members have collapsed beyond point C. And in case of status, it is less than IO only that you can set and measure. But this is sufficient to ensure that it is not yielded or failed. At that level, this table will help. And if you switch to the other output case, which is 2 times dBE, you can see this. In this case, many members started yielding 7, 8, 9. I think that is the last step. You can see many beams have yielded, but they're all safe, not collapsed. So this is expected. But let's select any member, any particular beam. And then if I go to the display, hinge results, you can see the hinge results for this beam. So this is for B2, or this is for the moment. You can see the backbone curve and the status of this force level in that beam. This will give that hinge level information you can get from this output. So other features are also available to get the table of format of the results, etc. So I will not discuss any further on that. This is for the 52 mm 2x dBE displacement, and the slope gives you that picture of members have started yielding, and there is no drop that represents there is no failure on the members. So interpretation of pushover analysis. I'm leaving to the individual to explore it further, but this is what we wanted to present. So all of the slides I have updated with key points that are required for the updates in the model. So which I already explained. I'm just walking you through the slides. So the demonstration of the base model and what we have obtained from this, and the design of LFR. This is the step 1. And we'll be running 2 scaled spectrum scaled forces for designing the lateral force resisting system, right? And then step 2, then part A is designing of the gravity frames by simply converting the linear lateral case to nonlinear static and specifying the displacement as target displacement, right? For that, we need to remove the participation of the lateral force resisting system. So in this example, I replace the actual property by none and then put roller supports to give the vertical support. But this is about the displacement. You can see the results here. And then the step 2B is studying the hinge formation with the lateral force resisting system, hinge definitions, assignments, and the nonlinear static analysis. Then twice the dB level displacement, we just saw. And important thing is no hinge formation in the gravity columns, either at the base nor at the roof. And also there are no shear failures in the beams. So I'm just bringing back the same slide, what we have introduced, and you can connect to this once again. Step 1 for the design of lateral system. Step 2 for the gravity frame design. And the third one is to ensure there are no premature failure of beams in shear and no hinges developed at the columns. Right. So that's all I wanted to present today's session. Let me know if you have any questions. I will try to answer them. Over to Lakshay.
Yeah, thank you so much, Vivek sir, and thank you so much everyone for tuning in. Vivek sir, there are some questions. If you could take a look at them, and then I'll post the Google form link for everyone. You can just put all of your queries if you have later after the webinar. We'll provide the recording of the webinar along with the slides and the FAQs by Monday or Tuesday. Vivek sir, over to you.
Yeah. Yes, Lakshay. Yes, there is a question. When we assign hinges to columns and beams, moments due to gravity loading will not be transferred to from beam to column. Yes, because we are primarily designing the lateral force resisting system, those identified as gravity frames will be uh, not transferring the force. So that's the idea of that. Yeah, even if large openings in the building, do we need? Yeah, we need to apply the rigid diaphragm. Yes, we need to, because we are releasing the frames, both the columns and beams for this. Uh, so we need to handle the degrees of freedom in those directions. So rigid diaphragm is needed in this case. So how the response spectrum converted into user load? Yeah, this is commonly done in for many applications. For example, foundation transfer. I think this response spectrum case is run, and then you'll get to see the story shears from the table output, and then the story shears, you can get the differences between the conceived stories. That will be the story force. Can easily get with the help of an Excel from the table output. Yeah, torsion is released in only one end. Yeah, that's how torsion is released. Yeah, we can see this. Yeah, yeah, we are providing the recording of the seminar soon. Okay. I think spectrum scaling is done with the spectrum cases in the base model, but I have removed them because there will be a lot of cases uh, which would be confusing if you have so much of list. So I removed them. Anyway, I'm not going to use them. So I kept only the scaled response spectrum. So scaling is done with the response spectrum case and EQX auto lateral load case. Usual way we do, and then finally once we converted into lateral forces, user-defined forces, I've removed those two load cases for simplicity. I think that is better to keep in that way, or else there will be confusions of multiple cases. So program is also capable of handling when you switch off certain cases. So the load combinations for those will not have the data, and it will give a warning, and it will continue to perform the design for the available load combinations. Right. So you can continue, but it is better that you simplify your load combinations for this, which I have done in the presentation model. Yeah, that 1.8 scale factor is for that. So um, so I wanted both unscaled and scaled user loads. So that's why that was in 1.8. So no cracked analysis for the floors. Why is it taking as no cracked analysis? In the nonlinear static case definition, it is also used for obtaining the long-term deflections. So in that, the cracked coming into picture, that's what it is. But in this case, we are not utilizing that. So roller support are to provide the vertical support at the locations where the lateral force resisting systems are removed. The modifiers, there are no change in modifiers. We'll keep them as the cracked section property modifiers for all the analysis for both lateral force resisting and also gravity frames. So if you find this exercise too long, but since you have introduced a very new concept, might be feeling so, but the bifurcation is the only key that we are going to do. One is for the lateral force system and another one is for the gravity. So when you do it, when you practice it, actually it doesn't take much of time, except for updating the load combinations and few other things and the definition of load cases and hinge assignments. But this exercise is required. So for floating columns, the same procedure can be applied, but floating columns, you will be reducing their stiffnesses or release their end moments. We will discuss it in another session on the floating columns, but the same concept remains applicable for that too. Yeah, 2 times the dB is equal to the MCE, you can say. That is explained in step number 3 of the slide, in our recommendation slide. Modifiers for gravity columns are same as the lateral force resisting. We maintain the cracked section throughout the analysis. So the rebar for the walls assigned is as per the detail that you'll do, any ductile requirements. So it is based on that. Just for demonstration purpose, I use 0.8 being a special wall. Yeah, the effect length factors for the column design, you can use the same effect length factor that you find in the base model and update it as a frame override for the column design. Yeah, pushover analysis is used to check the capacity. Yes, that is used. And especially for capacity design, it is required. So program is already having those features and built and ready to use. Temperature loads are not required for this. Are there any structural effects or concerns when column sizes vary across different floors in any regularly shaped building? Yes, there could be, and these kinds of study will reveal more such information from the analysis. Yeah, we can do gravity shear wall also. So in the base model, you can obtain some basic requirements like effect length factors, etc. And you can use it as an override in the other models. So quickly you can perform the designs. The focus would be more on the nonlinearity, yielding of these hinges, etc. But of course, yeah, design is also important. But the informations required should be obtained from the base model itself. So that's why I showed you the base model also, and then the other two for, for LFRS, and the other one is for the gravity frames.